Alright, so in this video I'll be showing you guys how I built this app. This app is called ClimateiQ, and it's actually built with a lot of features. Like you can see here, this is the dashboard, and over here you see the NA-CORDEX. You have the 25 kilometer resolution limit, then you have the ensemble mean calls to be 12. All right, then you have alert here, an alert feature here. This one says critical heat index exceedance in southwest US corridor projected plus 4.2 degrees Celsius above baseline by 2025 under SS, that's double SP5 to 8.5. Then over here you have the temperature. Here you have the model. This was actually built on data source, and I'm going to quote or refer to the data source that helped to develop this model as we progress along. Here you have the active regions, and then you have the score, you have the precipitation, bias, the ensemble, and then if you go over here, you see the regional map. Here you can actually tweak. These are animated tweaks for the NA North American CORDEX grid. So, and then here you can see the cell detail, all right, for the navigation. And then over here you have the precipitation, you have the task, you have the heat index, then you have the drought. All right, they all have color indicators. Then here you have the forecast. All right, you can see the SP double SP5 8.5, double SP3 7.0. And then of course all the way to the 1.0. You have about 4 categories, or rather 5, not 4, 5 categories here. So then of course down you have the projection controls. You can see here you can tweak them and position them in accordance to various variables. Then you have the milestones. All right, now let me quickly talk about this SP. This SP you're seeing here is actually the indicators that this particular app focuses on. Now let's really look at the impact. You have the impact assessment, the urban heat, the public health, agriculture, infrastructure, water resources, biodiversity. Then over here you have the policy response timeline, early warning system deployment, agricultural adaptation protocols, water infrastructure overhaul, carbon removal at scale, scenario evaluation. Then let's look at the model. All right, now the model itself is the backbone of this application. All right, it was trained on a data set which I'll be showing you very soon. Now this is the architectural block. Here you can see these particular variables that actually show how this model works, the convergence and then the speed matrix. All right, using 5k-fold matrix. Now you can also downscale. This is the downscaling section of this app. You have parameters, latitude, longitude, the scenario, the resolution, and as soon as you tweak these things and position them appropriately in accordance to the variable on ground, you can run the inference. All right, you can see the inference is complete. So this is the task, the TAS output grid that shows particular projection for that particular area. Then of course you have the alerts, which also shows different indicators. You have the critical extreme heat alert, you have the high, the drought risk escalation, then you have the medium precipitation sweep from Pacific Northwest. Now I must also state here that this app is actually dedicated to events within the North American corridor. So this is the mobile aspect, or the mobile version of the web that we've just seen. You can see almost everything is replicated in the mobile as well. As we can see, you have tabs there for the dashboard, then you have the regional, then you have the forecast, and then the impact, and then of course you have the model itself. So stay tuned as I go through this particular app and then tell you the new features that this app and what it's capable of. And of course we'll also be citing the data. This is actually the source of the data. That's the Canadian Center for Climate Modeling and Analysis, CCCCMA Earth Systems Grid Federation ESGF dataset. That's actually the source of data that the data was trained on, and the model, the AI model that was developed, was actually based on the data provided by this institution. So stay tuned, keep your fingers crossed, and let's just dive into this video to learn for life and not for school. Welcome to ClimateiQ, a scientific decision support system built on the NA-CORDEX North American Coordinated Regional Climate Downscaling Experiment dataset, providing statistically and dynamically downscaled climate projections at 25 kilometers spatial resolution across North America. Now, let's quickly look at the introduction and the purpose. ClimateiQ is actually a scientific decision support system built on the NA-CORDEX, that's North American Coordinated Regional Climate Downscaling Experiment dataset, providing statistically and dynamically downscaled climate predictions at 25 kilometers spatial resolution across North America. It is deployed in two complementary forms: the mobile applications for field and rapid assessment use, and a web dashboard for deep analytical workflows. These operational guidelines are written and developed for two primary audiences. Firstly are the practitioners, the climate scientists, hydrologists, agricultural specialists, urban planners, public health officers, environmental engineers, and secondly, policymakers, regional planners, government decision makers, infrastructure leads, adaptation strategists. Both audiences will find this platform specific workflows, decision frameworks, interpretation guidance appropriate to their roles. Now let's look at the core design principles. Decision relevance first. Every data layer and metrics is selected to support a specific class of regional impact decision, not to maximize data volume. Uncertainty to transparency. Confidence intervals in assembled spread and model scale scores are surfaced at every display level, so users understand what the data can and cannot assert. Multi-scale access. The mobile application enables rapid field-ready assessment. The web dashboard supports rigorous multi-scenario analysis and policy documentation. Reproducibility. All projections are traceable to ERA5 forcing data, NA-CORDEX model runs, and versions inference weights, enabling citation-ready reporting. Now, let's understand the ClimateiQ data. The ClimateiQ provides projections under 5 shared socioeconomic pathway scenarios, each representing a distinct future emissions trajectory. These are not forecasts. They are possible futures conditional on policy changes made today. Alright, so we have SP1 to 1.9, we have SP1 to 2.6, SP2 to 4.5, SP3 7.0, SP5 8.5. Then you have the columns radioactive forcing. You have the policy assumption we use in decision making. Now, you should always run these assessments under a minimum SP to 4.5, all right, the current trajectory, and the SP5 8.5 stress test, all right. Scenario, these are single scenario analysis systematically that systematically actually underestimates adaptation requirements. Now let's look at the ensemble spread and confidence intervals. ClimateiQ's projections are generated from a 12-member GCM global climate model. Ensemble, each member is actually possible realization of the climate system under a given SP forcing. The ensemble mean, that's the central line in all charts, and spread, shaded band, communicate uncertainty arising from model structural differences. Now, narrow ensemble spread, strong model agreement shows that higher confidence in the predicted direction of change. Now, for the wide ensemble spread, structural model disagreement, the direction may be confident but the magnitude is uncertain. Then we also have to take note that 90% confidence intervals, which is default, 9 of 10 ensemble members fall within the shaded band, widened to 99% for infrastructural planning, narrowed to 50% only for exploratory screening. Now let's take a look at the variables. We have the surface air temperature, the precipitation, the heat index, the drought index, that's PDSI, and then you have that's the abbreviation column coming next, then the unit and the decision relevance. You can see there that for surface air temperature, baseline for all heat stress, agricultural and health impact calculations are there. Then you have precipitation, flood risk, drought assessment, agricultural water balance, reservoir planning. Then you have the public health and outdoor worker exposure thresholds, that's for the heat index. Then you have the agricultural severity, water allocation, fire risk assessment. Now let's look at the AI model and built-in performance metrics. You have the R squared score as 0.9, that's about 92%. 93% of variance is observed temperature explained by the model. This is a strong, very, very strong predictive skill. Then you have the RMSE, it's at about 80%. The root mean square of 80, that's 80 degrees Celsius, is a typical error magnitude for any single projection. Then you have SSIM, about 80%, 88.1%, spatial pattern fidelity. Then the bias is minus 0.001, near zero mean bias, and model does not systematically over or under predict. That is, it has high reliability, that's what it means. Then the ensemble spread, plus or minus 1.20 degrees. This is actually irreducible scenario uncertainty at 2100 endpoint under SP 8.5. Now these are some of the screenshots of the metric, the AI models. You can see the graphs as related to the training. The force waste split was actually used, the train, the test, the validation, and the holdout respectively. Then you have the predicted versus actual TAS. Now following this is the AI model built-in performance metrics. You can see some of the graphs as well. 5-fold CV was used in the model performance across all splits. Now let's look at the AI model for built-in performance metrics. This is the generalization gap, and then here you can see the RMSE versus strain. You can see that there's an this is actually widely an industry standard acceptable range of generalization gap on unseen data. Now this is an example of the downscaling from the data used for this application. Now let's understand the software application. The ClimateiQ mobile application for iOS and Android web is designed for rapid field-ready assessment. It is optimized for single-handed operation, intermittent connectivity, and time-pressured decision context. Its 8 screens follow a logical triad to detail workflow. Connectivity note: the mobile app catches the most recent grid data and alerts locally. Core navigation and historical projections are accessible offline. Live downscale inference requires an active internet data connection. Now let's interpret the 6 key performance indicator cards. You have the KPI card in the first column. This is about 2500 SP5. This means end of century temperature anomaly under worst case scenario. For the action trigger, if the temperature is higher than 4 degrees Celsius, the recommendation is to escalate to stress test impact assessment. With the model RMSE, is the current folder error. It's lower the better for the RMSE. If RMSE is actually 1.2 degrees Celsius, treat projections at screening level only. Active regions: number of NA-CORDEX cells currently being monitored. Confirm coverage includes your area of interest. Then you have the R2 score, that's the R squared score, overall model explanatory power. If R squared is less than 85%, flag uncertainty in any formal report. Now let's look at the precipitation bias. Systemic over-under prediction of rainfall. This actually would mean negative bias, means the drier than observed. Adjust water planning accordingly. It's the recommendation. And the ensemble spread, that's the irreducible uncertainty across the 12-member GCM ensemble. Spread greater than 2% variance. Multi-scenario planning. Switching climate layers. Use the 4-layer buttons, that's the TAS, precipitation, heat index, drought at the top of the screen to change the variable being displayed. Each layer uses a dedicated color ramp calibrated to the variable's physically meaningful range. As you can see here, you have the layer TAS, the blue, teal, yellow, which means the red cells are the highest temperature anomaly. Prioritize for heat stress and health impact assessment. For the precipitation, you have the red to orange, yellow to teal blue. Red cells indicate drying, blue cells indicate increased precipitation. Both carry flood and drought risk. Alright, so then you have the heat index, blue, yellow, orange, deep red. Cells above the yellow orange boundary exceed OSHA, ILO, outdoor work threshold in the predicted future. Drought, teal yellow, orange red, dark red. Dark cells indicate severe PDSI deficit. Critical for agricultural and water resource planning. So let's look at the SSP forecast interpretation. The forecast screen displays the full 2005 to 2100. That's over 75 years ahead. Temperature projection trajectory for all 5 SSP scenarios simultaneously. This multi-scenario view is the primary tool for communicating climate risk range to non-specialist audiences. Using scenario chips, toggle scenarios on and off using the chips at the top of the screen for the most decision context. The following combinations are recommended. You have 3 columns here. The decision context is recommended scenarios, rationale. Alright, so then you also have the infrastructure design line as 30 years, SP 4.5 to SP 5 to 8.5. And the rationale is central and worst case bracket for long-lived assets. Then successively you have the agricultural seasonal planning and the public health preparedness, the policy scenario analysis, the rapid stakeholder briefing. They are recommended scenarios and the rationales respectively. Let's look at the impact assessment workflow. The impact assessment screen translates temperature and precipitation projections into sector-specific vulnerability scores for 6 domains. This screen is designed for rapid cross-sector triage, identifying which sectors face the highest exposure in a given region. Reading the sector cards. Each of the 6 sector cards displays a risk classification: critical, high, medium, low, 8 to 0 up to 100 vulnerability index, the summary impact statistic. The risk classifications are calibrated to SP to 4.5 central projection. Critical risk requires immediate prioritization, activates sector specific contingency. Then of course, subsequently, you also have the descriptions for the high risk, the medium risk, and the low risk respectively. So following this is the live downscale inference. The downscale screen runs the CNN LSTM model in real time against user-specified geographic coordinates, scenario, and resolution. This is the most computationally intensive screen, and it requires an active data connection. So step-by-step inference protocol. You can set the latitude and longitude using the sliders by consulting the regional map for coordinates of interest. Precision to 0.1 is sufficient for 25 kilometer grid resolution. Select the scenario appropriate to your decision context. See previous section for guidance. Set resolution. Note that final resolution 12 kilometer has higher computational cost and slightly wider confidence intervals due to increased spatial heterogeneity. Then of course, tap the run inference. Typical inference time is 1.5 seconds. You don't have to navigate away during the processing. Then the output task grid shows spatial temperature anomaly distribution centered on your specified coordinates. Then the warm color cells indicate highest local anomaly. You can screenshot the result for inclusion in site assessment reports. Accuracy note: inference output represents the model statistical downscaling of GCM forcing data, not a physical simulation of local microclimates. For urban heat island and assessment, apply a 1.5 degrees Celsius to 4.4 degrees Celsius urban penalty displayed by impact assessment to the downscale task value. Alert management. The alert screen displays a live feed of system generated climate threshold exceedant events sorted by severity. The alert badge on the navigation sidebar indicates the number of unread alerts. Alert severity control. You have like 4 columns described under this particular section. The first column is the severity, then the second column is the threshold basis, recommended response time, and finally the escalation path. Then for the rules, you have the critical, high, medium, and info respectively. Now let's look at the web-based dashboard. This is the operational guide for the web-based interface, because this program has both software and hardware, or rather it has both web and mobile. So you have the ClimateiQ web dashboard, which is the primary platform for rigorous analytical workflows, multi-scenario comparison, model diagnostic review, and the production of citation-ready outputs for formal policy processes. It provides the same underlying data as the mobile application with substantially deeper analytical capability and export options. For the recommended environment, Chrome 12 or Firefox 121 at 1440 by 900 minimum resolution is recommended. And for presentation to stakeholders, use full screen mode F1 with the sidebar collapse via keyboard shortcut Alt B. Now let's look at the dashboard overview KPIs. On first load, the web dashboard populates all 6 KPI cards: the task anomaly chart, the model performance, and the panel simultaneously with parallel asynchronous data fetches. All right. Initial load time is typically under 500 milliseconds on a standard broadband connection. Session start checklist. Confirm the RMSE KPI is less than 1. Values above this indicates recently retrained model that may have slightly different spatial bias characteristics. Check the ensemble spread KPI if spread exceeds plus or minus 1.5 degrees Celsius, so you can widen the planning ranges in any formal assessment produced during this session. Review the alert banner. If a critical alert is displayed, navigate to the alerts screen before beginning analytical work to ensure your session is contextualized by current conditions. Confirm R square is greater than or equals to 90% before relying on spatial pattern analysis on the regional map. The task anomaly chart, web-specific features. Over any point of the chart to see year-specific values for both historical era 5 and predicted anomaly. The vertical reference line is interactive. Click and drag to change the reference year shown in the forecast milestone table. The historical period pre-2025 uses era 5 observed data. The projected period uses ensemble mean. The crossover point is clearly marked. Now for the performance panel, you have the 5 progress bars in the right panel, which represent the model's validation and performance across the training, validation, and test splits. These are not to be confused with the scenario uncertainty. They represent the model's skill at reproducing known historical observations. Alright, so this is very important. And let's move on to the next section, which is the regional map, the deep analysis. The web implementation of the regional map is optimized for systemic spatial analysis across the multiple grid cells, supporting region-wide assessment workflows that will be impractical on mobile. Alright, now let's take a look at the layer-by-layer spatial analysis protocol. You can begin with the task layer to identify the broad spatial pattern of temperature anomaly across the study area. Switch to precipitation to identify regions experiencing concurrent precipitation changes. Cells showing high task anomaly and precipitation declines are compound risk zones. You can flag these immediately. Switch to heat index to identify where temperature humidity combinations will exceed human physiological thresholds. Switch also to drought, that's a PDSI, to access water stress in the agricultural and hydrological context. For each layer, systematically click on the top 5 highest anomaly cells, visible as the darkest red, to populate the cell detail panel. You can also use the view detail modal to export to the cell PDF or CSV reports. Okay, now let's look at the grid statistics panel interpretation. The grid statistics table, that's the right panel, provides statistical distribution across entire visible grid extent. The key values to track include the mean task versus the maximum task gap. A large gap that's greater than 2 degrees Celsius indicates high spatial heterogeneity. Localized hotspots that warrant targeted site assessment. Now the percentile, if the grid mean sits below the 40th percentile, the region is experiencing sub-average precipitation. You can also change this to relative to the full NA-CORDEX domain. Now let's look at the forecast module and scenario planning. The web forecast module is the primary tool for formal scenario planning and stakeholder communication. It combines interactive multi-scenario visualization with configurable statistical tools, multi-scenario comparison workflow. Activate all 5 SSP scenarios using the cheap toggles. This provides the full envelope of the plausible features. You can set the horizon year slider to the endpoint relevant to the decision. That's for instance 2055 for a 30-year project. You can read the projected temperature range at the horizon year from the chart. The vertical spread between SP1.9 and SP5 at 8.5 at their year is the policy. Now, controllable uncertainty. This is the range over which mitigation decisions have leverage. You can toggle off SP5 8.5 to see how the project or the projection rather changes under moderate mitigation. That's the SSP to 4.5. The difference quantifies the climate benefit of the Paris Agreement pathway. You can export the current project's projection as a CSV using export button for inclusion in formal assessment reports. A milestone table. The milestone table SP5 to 8.5 by default identifies the years by which specific temperature thresholds are crossed. These milestones are the canonical reference points for time-sensitive adaptation decisions. 1.5 degrees Celsius 2030 Paris Agreement threshold monitoring and early warning system should be operational by this date. 2 degrees Celsius, that's 2025. This is critical infrastructure review threshold. Assets designed before 2000 should be assessed for climate compatibility by this milestone. We're talking over 3.2 degrees Celsius by 2060. Ice sheet as the ice sheet instability zone, and the sea level rise projections become material for coastal infrastructure. 4.5 degrees Celsius by 2075. Cascade risk zone, multiple simultaneous sector stress likely. You can compound the impact assessment required here. Now, finally, there you have the 5.0 degrees Celsius, that by 2100. SSP5 8.5 endpoint used only for long-term infrastructure design and sovereign risk planning. Impact assessment and policy pathways. Now, for the web impact assessments, this provides the same 6-sector vulnerability review as the mobile app, with additional workflow integration for the policy documentation processes. So you can see the sectors, about 4 columns here. You have the sector, you have the key impact metric, relevant policy lever, decision or respectively. Then for the roads, you have the urban heat, agriculture, the water resources, public health, infrastructure, and biodiversity respectively. And you can see typical descriptions for each of these items. Now, for the model diagnostic quality assurance, the model screen gives practitioners and data stewards direct access to the CNN LSTM model's architecture, the training history, and the validation statistics. This screen is essential for quality assurance reviews before any formal policy submission. Alright, pre-submission QA checklist. Verify that 5 folds pass as the green pass tag. A failing fold indicates the model may have poor skill in a specific temporal period. Check the mean RMSE now row. If the mean RMSE is greater than 90%, add a model uncertainty to civet any formal report produced in this session. Now, inspect the loss convergence chart. Chaining and validation curves should track within 10 to 15% of each order at convergence. Alright, widening divergence at late epoch indicates overfitting. Review feature importance. Okay, the Z500 potential and SST anomaly should be collectively accounted for about more than 50% of the explained variance. If a single feature exceeds 60%, flag for model review. Record the model version displayed on the header tag in all exported reports. Now, the architecture summary for non-technical stakeholders. When briefing non-technical decision makers on model trustworthiness, use the following plain language summary. Briefing language. ClimateiQ uses a 2-stage machine learning model. The first stage, CNN learns spatial patterns in the atmosphere, similar to image recognition. The second stage learns how those patterns will evolve over time, similar to predicting text. The model has been validated against 40 years of observed climate data, explaining 92.3% of observed temperature and variation across North America. Now let's look at this downscaling inference engine. The web downscaling screen provides the same live inference capability as the mobile app, with the additional advantage of a larger display for spatial pattern interpretation and direct integration with the export pipeline. Systematic site assessment protocol. Set the target coordinates to the centroid of the geographic area under assessment. Run inference under SSP 2 to 4.5 first. This establishes the central planning baseline without changing coordinates. Switch to SSP 5 to 8.5 and run again. The difference between two output grades is the policy controllable risk minimum. Quantify this for inclusion in the cost-benefit analysis of adaptation interventions. Now run at 12 kilometers resolution for site level assessment, 55 kilometers for regional planning, 50 kilometers for national policy. You can also screenshot each output grid and include in assessment documentation with the full parameter set as the latitude, longitude, scenario, resolution, and time spot or timestamp rather, respectively. So let's move on to the next stage. This is decision frameworks for practitioners. This section provides structured decision frameworks for 6 practitioner domains. Each framework maps ClimateiQ screen to specific analytical tasks and specifies the outputs required for professional practice. You have agricultural impact assessment. The purpose is to quantify projected changes to crop productivity, water demand, growing season length for a defined agricultural region. Then you can see here the decision for practitioners. You have the step, the platform, the scoring, the action, interpretation. Now for the first one, it says either the screen is regional map. This is the action and the interpretation. The set layer to task, identify cells. And for the second one, you have regional map again. We switch to precipitation layer, cells showing concurrent drying, red, orange. Then the third one, web forecast. Okay, that's the either stands for both either the mobile app or the web app, right? Now for the third one, you have specifically the web. And if the screen is forecast, its meaning is that you set the horizon to 2050, typical agricultural policy horizon. All right, document projected anomaly range across SSP 1 to 2.6, SSP 2 to 4.5, and so on and so forth for the southern region. Now for either the web and the fourth step, now either the web or the mobile, if the screen is under the impact assessment, you can record the agricultural sector vulnerability index to yield the impact statistic. Cross-reference with regional crop statistics from national databases. Now for the web, if the screen is downscaled, run inference at SSP 2 to 4.5 and SSP 5 to 5.8.5 at 12 kilometers resolution. Web regional map, export per cell CSB for top 10 high risk cells in the zone. Include the formal agricultural climate risk report as well. Now let's move to the next stage here. This one is saying urban heat and public health assessment. The purpose is to identify urban areas exceeding human physiological thresholds and quantify projected heat mortality exposure. Now if you open the regional map, then you go to the heat index layer. Urban grid cells in red represents areas projected to exceed 40 degrees Celsius apparent temperature for a greater than 20 days per year by 2050 under SSP 2 4.5. Cross reference with urban heat sector card in impact assessment. The 3.8 degrees Celsius urban penalty applies to all downscale task values in urban cells. Ensure this adjustment is explicit in any public health report. Use the forecast milestone table. the 2.0 degrees Celsius global mean milestone 2045 corresponds approximately to a plus 5.8 degrees Celsius peak urban heat index in North American megacities under SP 5 8.5. For public health practitioners, you should know that this anchor heat emergency protocols to SSP 2 4.5 projection, which indicates conservative planning, while using the SSP 5 8.5 values for maximum capacity design of cooling centers and emergency services, respectively. So in the next aspect of this app here, description, we have the water resources and hydrological assessment. The purpose is to actually project changes in precipitation regimes, drought severity, stream flow for water allocation, and infrastructure planning. You can begin with the regional map, precipitation layer, identify the spatial extent and magnitude of projected precipitation decline across catchment of interest. Switch to drought as PDSI layer, cells below the midpoint of the scale, yellow-orange boundary, which indicate PDSI values approaching 2.0, which represent moderate drought. Cells in deep red represent severe drought, that's PDSI less than or minus 3. Use the impact assessment. The water resources card, 22% summer streamfall is the headline figure for SP 2 to 2.5. For SSP 5 to 8.5, apply a 1.4 times multiplier as a conservative planning factor in the absence of sector-specific scaling. Reservoir field modeling should use the full ensemble spread, that's plus or minus 1.2 degrees Celsius, to generate upper and lower flow scenario bounds, not just the central projection. So we move to the next aspect of this app, which is infrastructure and the environment assessment. Infrastructure designers should select the SSP scenario matching the design life of the asset. A bridge designed today for 75-year service life, endpoint as 2100, that's 2100 year, 2100 AD, should be assessed under SSP 5 8.5. Alright, the forecast milestone table provides threshold crossing years for 1.5 degrees Celsius plus 2.0 degrees Celsius plus 3.2 degrees Celsius, and then plus 4.5 degrees Celsius and plus 5.8 degrees Celsius respectively. You should match these to material performance degradation curves for the asset class. Use the infrastructure sector card in impact assessment. The plus 45 heat days above the road surface buckling threshold is the headline figure. This translates directly to increased maintenance cycles and early replacement costs. For energy grid planning, run downscale inference at the location of any major generation and transmission assets. Okay, then the high task anomaly at these locations increase cooling demand, and while potentially degrading thermal plant efficiency. So we move to the next aspect now, which is the infrastructure and built-in environment assessment. The purpose is to assess climate stress on existing planned physical infrastructure assets, including roads, bridges, buildings, and energy systems. Decision frameworks for policymakers. Policymakers interact with ClimateiQ primarily as a source of scientifically credible, spatially specific evidence for adaptation on planning, budget, and allocation, respectively, and of course, cross-sectoral coordination. This section provides frameworks calibrated to policy time scales and decision types. So the rapid briefing protocol, this is about less than 30 minutes for time-constrained policy briefings. Use the following condensed workflow on the mobile application. The dashboard, note the delta temperature key performance indicator and the active critical alert. These 2 points establish the urgent framing for the briefing. The regional map tasks like take a screenshot of the spatial extent of cells in the orange red, that indicator, that's the anomaly that is greater than plus 3 degrees Celsius. This is the visual anchor for the briefing. Then for the impact assessment, you should identify the two highest risk sectors, that's the red orange cards. Focus the briefing on the narrative of these two sectors only. The breadth reduces the salience for busy decision makers. Now for the forecast, set to SSP2 4.5 to SSP5 8.5 to show the range, not the worst case alone, just to avoid fatalism and to demonstrate that the policy choices affect outcomes. Alright, so we move to the next thing now, which is the annual adaptation plan development. For formal annual adaptation and planning cycles, the web dashboard should be the primary platform. The recommended sequence is as follows. You have the phase, there's about 3 columns there. You have the phase, the ClimateiQ action, then the policy output. Alright, for brevity, we're just going to look briefly at them. You have the baseline assessment with about 5 rows there. You have baseline assessment, the scenario framing, sector prioritization, the pathway development, and the QA and sign off respectively. So quickly, let's just move at the next item here. You have the publicity or the public communication of climate risk. When using ClimateiQ outputs in public-facing communication, the following principles apply. Always present a minimum of 2 scenarios. Single scenario communication, especially worst case only, which is scientifically can be misleading actually and may reduce public trust. So you should also always present at minimum 2 scenarios. All right, the single scenario communication, which is scientifically misleading and may reduce public trust, or use the SP2 to 2.5 or 4.5 rather. Central projection is the baseline narrative. Frame is 5 to 8.5 as what happens to what if we do not act. Now, this can be put under this category, and SSP1 2.6 as what becomes possible if we do. So these are probable approaches to what this app generates. Now lead with regional scientific impacts. That's for instance summer stream flow, the river Nile basin is predicted to decline by 22% rather than global temperature averages, which are not directly decision relevant for local populations. Always disclose the model version, the validation R squared, the data vintage, and the publishing ClimateiQ sourced figures. So do not round ensemble spread, reporting plus 3.2 degrees Celsius without the plus 1.2 degrees Celsius ensemble spread. Alright, these are just guidelines towards public communication of climate risk. So we now move to the cross-sectional coordination protocol. The climate impact rarely respects sectorial boundaries. ClimateiQ's impact assessment screen is the primary coordination tool for interagency climate risk dialogues. The facilitation guidance in multi-agency workshop projects the impact assessment screen on a shared display. Walk through the 6 sector cards sequentially, with each sector leads agency responsible for interpreting and committing the display's risk level. The policy timeline then becomes the negotiated action plan. Compound risk identification. There are situations where 2 or more sectors simultaneously experience high or critical risk requires escalation above normal sectoral planning channels. ClimateiQ simultaneous sector display makes compound risks immediately visible. So let's really move to the next aspect here. You have the data export and reporting. Both platforms provide structured report capabilities. All exports are timestamped versions and include the full parameter set used to the data, okay, enabling downstream reproducibility. There you have the export type, the platform type, the screen, and the content. and the descriptions that actually match each of the rows, like the projection CSV, the cell detail PDF, the cell detail CSV, projection markdown, and the full report respectively. So these are very key notes to be put in mind. So let's go now to the platform comparison using the case scenarios, use case routing. Now you can see 3 columns here: the compatibility or the capability rather, and the use case, the mobile app, and the web dashboard. You can see that the web dashboard has much more features than the mobile app. All right. So then the model, how the model is actually tuned to this operation, to the live use of this application, is also indicated on this table. So quickly, let's go to the next section, the uncertainty communication. Effective use of ClimateiQs requires an accurate mental model for the sources, magnitudes, and implications of the uncertainty in the projections. This section provides a practitioner-ready taxonomy of uncertainty sources and communication strategies. The key principle is that uncertainty about the magnitude of climate change is not uncertainty about its direction. All SSP scenarios, okay, that's the key indicators, show warming above the 2025 baseline. All right. Communicating uncertainty should never be used to imply, therefore, we might not need to act. So this is just a brief table that describes guidelines towards this. You have the uncertainty source, the magnitude, ClimateiQ, the reproducible, indication whether it's yes or no, then the communication strategy. So in the next stage of this explanation, we have the limitations and responsible use. Now, we should bear in mind that ClimateiQ is a decision support tool. It's not a substitute for full physical climate modeling, engineering, due diligence, ecological survey, or legal and regulatory compliance assessment. The following limitations must be understood and disclosed in all formal use of this platform. The technical limitations: spatial resolution. The 25-kilometer grid cannot resolve the features smaller than the approximately 50 kilometers, the 2 grid cells. Urban scale heat dynamics, the small river catchments and highly localized precipitation events require supplementary analysis. Variable coverage. ClimateiQ provides stars, PR, high, and PDSI. It does not externally provide wind speed, humidity profiles, wave height, performer force extent, or wildlife risk indices. Sector assessments requiring these variables must source them from complementary datasets. Temporal coverage. The projections begin at 2025. Historical period data, that's 1980 to 2024, is ERA5, that's reanalysis, not station observation. Station-specific analysis should cross-reference with National Meteorological Agency's records. Alright. Bias correction. The CNN LSTM model applies implicit bias correction through training. Residual biases, mean bias 0.001 degrees Celsius, RMSE 0.847 degrees Celsius are small but non-zero. Do not round RMSE to 0 in formal reporting. Then, of course, the appropriate versus inappropriate use of this app. In the appropriate uses, you have regional scale climate risk screening. Then you have the multi-scenario adaptation planning, the sector vulnerability prioritization, then the stakeholder and policy communication, comparative analysis across regions, education and capacity building. Now, let's go to the inappropriate uses. Site-specific engineering design, use physical model, legal liability or insurance underwriting bias, operational weather forecasting, sole basis for emergency evacuation decisions, replacing ecological or hydrological surveys, attribution of specific extreme events. So these are just general guidelines for appropriate and inappropriate uses. So we now go into the data governance and attribution. All ClimateiQ projections are derived from NA-CORDEX and ERA5 data under the open data licenses. Commercial use of exported data is subject to the terms of those upstream licenses. Any publication using ClimateiQ's outputs must both cite the ClimateiQ platform version and date and the upstream NA-CORDEX data sites. Projections should not be represented as official government climate projections unless the relevant National Meteorological Service has formally endorsed the platform for that purpose. So we now look at the citation. Of course, all formal publications and policy documents using ClimateiQ's data should include the following citation: ClimateiQ version 1 2026, regional downscaling projections for Earth data, dataset courtesy Earth System Grid Federation, NA-CORDEX Ensemble, N12, CNN LSTM model, R squared 0.923, RMSE 0.847 degrees Celsius. Of course, you have the author and the organization involved, the developer contact. So thank you all very much. Hope you enjoyed this presentation. Cheers and all the best.